Hi, my name is Raziel. I lead TensorFlow model optimization, and today I will talk about our toolkit and in particular about techniques around quantization and neural connection pruning. So first I'll introduce what is model optimization, what is our toolkit, and then reason about why we think it's important, why we're investing in this area. Then I'll cover the tools that we have available, and at the end I will give an overview, a quick overview on about our roadmap for the short term and the longer term. And hopefully at the end of the presentation we still have some minutes to go over a Q&A. So our toolkit implements techniques that should allow you to optimize machine learning models for deployment and execution. We think this is important because machine learning is everywhere, right? It's a very important field, and we think that there is a lot of room to make it more efficient, and this has some implications, both like economy, like you can make all these applications much better, right? Like the quality, or cheaper to execute. But also we can enable some new models and new deployments and new products that otherwise are not possible, even if you just try to do execute these machine learning models on servers, right? So currently machine learning runs either on the server or on the edge. On the server, you may think that there is a lot of capacity, there is a lot of compute and memory. So, what is the benefit of optimizing these models? Well, applications are still, bound by latency. There is still a very important metric for a lot of applications. Or you want to improve the throughput, right? How many tasks can run on your server? And these two are also directly correlated to money. Right, so everybody will want to save money, and potentially we're talking a lot of money. Now, on the edge is a little bit more obvious why we need optimization, right? It's a very resource-constrained environment, even if you're talking about applications in general. We need to deal with, reduced memory, compute, power consumption is typically an issue. Bandwidth, both downloading models from the cloud or even within the chips to be able to transfer parameters from memory to the processor. This could be a problem if the model is too large. Plus, we have a wide variety of hardware, more than in the server, and we need to make sure that these models run efficiently on all these different types of hardware. So it follows that if we are optimizing these models, then we can have better models, and then eventually it starts translating in enabling new products that otherwise couldn't exist if we just were running these models on a server. And this opportunity is larger than just on smartphones. Machine learning is it's trickling down into more environments. We have machine learning models, for example, that are used to detect failures in machinery in factories, or we use it in self-driving cars. We use it in the office to scan documents and try to understand them. And just to give you some numbers, right? Like the size of the smartphone market is really a fraction of the potential for the edge devices in general. So basically, the two reasons is we want to make machine learning more efficient. It's already very important for the servers, but it's pretty crucial for embedded devices. So we started this toolkit about a year ago. We initially launched post-training quantization with this hybrid type of quantization, and I'll go in more detail later in the presentation. Then earlier this year, we launched the API for neural connection pruning. Then we created this specification of quantized operations, integer quantized operations for TensorFlow Lite, and we launched also post-training quantization support targeting this specification. More recently, we added support for reduced float precision, and hopefully soon we're going to be launching quantization-aware training API, and also adding support to TF Lite for sparse computation. So now I'll go into these techniques and these tools in a little bit more detail. So let's start with quantization. But first, I think it's important if we have some at least basic understanding of what is quantization and why it's hard, and why we are approaching our tools the way that we're doing it. So let's start with a simple example. Matrix multiply, it's a basic operation for machine learning models. Right, you have two matrices, two tensors, A and B, and then you do some multiplication, accumulation, and you get a third tensor C. Right? So each tensor is just a bunch of values that produce the third tensor. Then just a little reminder about how matrix multiply works. So each one of these results of the tensor C are computed as multiplications and accumulations. So if we look at one of them, then if we think how we're training these models, typically in a higher precision, let's say float 32, then it follows that the operands of the multiplications are float 32 in precision, and then the product will be also a float 32, right? And then the accumulation will be also float 32. So this is fairly straightforward. There is some loss in precision, but machine learning is pretty good at dealing with it, at least at this level of precision, so no problem. Now, what does this have to do with quantization? Well, let's go back to what were our goals for optimization, right? We want to be able to address all these restrictions. And also we want to be able to deploy in as much hardware as possible. So a common thing that we do is let's reduce the precision that we operate in. Right? Let's say, for example, go from the 32-bit floats to 8-bit integers. And then let's operate, let's say, entirely with integer operations. And this will be good because then, we are going from 32 bits to 8 bits, so we reduce the memory. The models are 4 times smaller. Then integer operations are typically faster to execute. Then they are also consume less power. And then because the parameters and also the dynamic values, the activations are smaller, then we reduce bandwidth pressure, right? It means that in the pipes and the chips, then there is more room for things to flow around, which can also translate in faster compute, reduced power. And then integer operations tend to be a fairly common denominator across hardware, right? CPUs, DSPs, different APUs, they support the integer operations. So, okay, so we said we're going to reduce the precision. So how do we convert the 32-bit float to 8-bit integers? Well, we do something right now. We do something very simple, right? So we have this linear mapping where we say, okay, we take the values from a tensor, we compute the minimum and the maximum value, and then based on that, we spread them evenly on the 8-bit range. Basically, it's very simple, right? So is that all that we need to do? Well, I wish. So it's not that simple, right? So let's go back to the example. So we have the matrix multiply, and now let's say that we quantize the values, right? And they are already 8-bit integers. So the operands in the multiplies are 8-bit integers, and then the multiplication, the products. Now you need 16-bit to represent it. And then you need to accumulate, and you probably want 32 bits to accumulate on that, right? So what is the problem? Well, the problem is that now you have tensor C full of 32-bit values, and that is not great when you want to fit that into another matrix multiply that you really want to execute this as 8-bit integers, because we already talked that it's so efficient, right? So what you do, so you scale them back down, right? So you just sort of quantize them on the fly now, back down to 8-bit integers. So then you can feed them to your 8-bit matrix multiply and all good. But what are the implications of all this process? Well, so it means that we're changing the static values, right, the parameters, the weights. We are changing also the dynamic values, the activations, because we're scaling them, quantizing them on the fly. And it also means that we are changing the computation, right? In this case, very simple example, we just added a scaling operation, but it can be a bit more involved. So you could say, okay, that doesn't seem that hard, right? Like we just added another scaling operation, and it's just easy, right? Well, some math is a little bit more complicated than that. This example actually is from layer normalization of an LSTM. And this one, aside from looking a bit more complex, is it's an example where if you just apply these naive rules of operate, rescale, you actually end up in sort of a numeric black hole where scales cancel each other, and basically just things don't work if you just go naively about it. And then it's more complicated because in your decisions about how you're gonna represent this computation in integer form, quantization, we want to be efficient, so lower precision is good, but we also want to be accurate, which means lower precision is bad. So it's a lot of trade-offs that you have to do. Then further complicating things is we have heterogeneous hardware, right? There is all different types of hardware with different capabilities, right? Different operations that each hardware supports, and also different preferences. Some hardware is, better executing, operations, say, in reduced float, or with different bit widths or different restrictions. So, and we want to account for all those things when we are creating our quantized recipe or quantized program. Then there is the fact that machine learning, is hard to interpret. We don't understand it, right? Like we don't understand how it works. Not to the level that we can have good proofs to know that a transformation that we're doing to this model, to this program, will actually work or not result in a catastrophic error, right? You don't want to take a model, you quantize it, and then this model suddenly starts giving you some weird results. So it makes it a little bit much more complicated to define these transformations. And then finally, I will say that this is all more complicated because the model is not enough, the program is not enough. Depending on how the quantization is defined, you might also need some extra data. So in the example of the matrix multiplier, right, we needed to compute the minimum and maximum values of the dynamic activations, right? And that only can be done if we run inferences through the model, right? Which means that you need to provide some representative data. So basically, it's just another hurdle that you have to account when quantizing these programs. So, basically this means that when we talk about quantization, we're really talking about rewriting, transforming this machine learning program to an approximated representation based on the operations that you have available. So now, how are we addressing this in our toolkit? Well, the first thing that we decided to do was try to scope down the problem and say, okay, we're going to define specifications that for common operations, like in this case is a diagram for a convolution, have a well-defined quantization behavior, right? So we know that now with this information, this low-level information that is relevant to quantization, then hardware can target those specifications, and then our tools can target that specification. And then we can all work at this level. And then we also get the other benefit that from the user point of view, you can quantize a model, and then this model can run in different hardware without any change. So right now, in our toolkit, we support 3 different quantization types. I'm including here reduced float as a quantization type, but it's just a much simpler thing where we just typically go from float 32 to float 16 parameters and computation. So that's pretty straightforward. The next one is our hybrid quantization, which basically makes use of 8-bit for the parameters, biases and activations. We leave as 32-bit floats. And then we try to be as smart as possible for how we execute this program. So the goal being that For example, heavy operations like big matrix multiplies are left in the integer domain, and then we use floating point for things like activation functions. So it's a nice trade-off between accuracy and performance and optimizations. Then the third one is integer quantization. This means everything is integers. All the parameters are integers, and all the operations are integers. This is obviously the more complicated one. So the benefits of the reduced float is, well, you guess your models are now half size. And then depending on the hardware support, you might get some speed ups. And then the accuracy losses tend to be very minimal. Pretty much always works. I haven't seen myself, at least, an actual model that doesn't work in Float 16 that was trained in Float 32. Hybrid quantization then pushes it further. You now get 4x reduced in size, and then depending on the computations, the operations that you are using, you may get different performance improvements. It tends to be larger for fully connected models or RNNs. And then the third one is the only integer quantization, so it has the same benefits as hybrid in terms of memory size, but is faster to execute. And it has a great advantage that it has more hardware coverage. So for example, typically MPUs, some of them are only like integer based, like over HTPU. Now, let's talk about the tools to actually quantize those models based on those quantization types. So we have two types of tools. One that works post-training, so it works directly on the trained model, and the other one that is work in progress is during training. So let's talk about the post-training. The process is very simple. You basically assume that you just have a trained model. It doesn't really care how you train it. You just have a TensorFlow model. Then currently via the TensorFlow Lite converter, you just convert this model to TensorFlow Lite and quantize it on the fly. And then you just have a model that you can execute on whatever hardware is supported in that quantization type. So now let's look at the specific quantization types. So the first one, reduced float, is you just set a couple of flags. You just say, use the default optimizations, and then the type that I am targeting is float 16. And then basically this will take care of changing all the parameters and the computation. And again, depending on the hardware that you're running this model, you might get a speed up right now. For example, GPUs support float 16 natively, so you might get some speed up there, either because of the computation or even just because of the bandwidth in your chip will be reduced. Like I said, benefits, well, the size goes to half, and the accuracy drop is very minimal. Is, I will say, within the noise. Then the next one is our hybrid quantization. So again, this is very easy. You just set the flag. Now this is the default for the TensorFlow Lite converter. You set it to default, and then again it will make sure to quantize all the parameters, and then operations that doesn't have yet a defined specification for the quantized form, it will be kept in the original precision, and then you will get some speed ups, and you will be able to execute in whatever hardware complies with that specification. So typically this one works pretty well for CPUs. And again, benefits, 4x compression for the models, and then you get some speed ups. All these are convolution-based models, so that's why the speed up is not as big. And I would say these are 1-year-old numbers, so probably right now is faster. And the same for accuracy. So accuracy is pretty good, and actually that's we're working on some changes. So for convolution models, it will even be a bit more accurate soon. Then the third one is the integer quantization, right? So this one is the one that is a bit more complex because now you need to provide some data, right? So you say, okay, I want to optimize a model. but I want to use the integer quantization, so now you need to provide some data. And by data, I mean unlabeled samples of what your neural network will typically see in reality, right? So if it's an image processing model, you need to feed some pre-processed images. And we're not talking about a lot of data. For the results that I'm going to show next, we're just talking about 100 samples. That works pretty well. So it's a bit more complicated, but it's not very complicated. So these are some results from post-training quantization across different models. As you see, for the majority of models, the loss is not that big with respect to the full precision train baseline. The only one I will say is the mobile SSD model. So that is a bit more meaningful drop. But again, a variety of models work pretty well with post-training quantization. Now I'll talk about during training because, like I showed in the previous results, there is still some models that will benefit from doing this training, quantization-aware training. And by quantization-aware training, we mean we try to emulate the quantization operations, the quantization losses during the forward pass of the neural network with the hope that the parameters will be tuned to account for that. So the process for doing the quantization-aware training for using our API, it's a little bit more involved, but we are, again, trying to make it very simple. So we build this API in Keras, again, to make it very easy to use. So basically, we assume that you already have a Keras model, and then you just need to call our API to apply the quantization. So, and this might change a little bit, but it will look something like this. So you just have a model that you already built using Keras layers, and why not? And then the only thing that you need to do is call our API on your model. Then you get now a model that is rewritten to have all the emulation of quantization. And then you just call your fit function. And that's it. So then you just train your model as usual. And then you can go through the TensorFlow Lite converter, and then it will take this model that was trained with quantization. It will have all the data necessary to quantize it, and then it will produce a quantized model that now, just like the post-trained model, you will be able to execute in different hardware. These are some numbers from quantization-aware training, preliminary numbers. If you see the delta is a little bit better than post-training quantization, it's not a very big difference except for the mobile SSD. So before it was 4% for post-training quantization. In this case, it's 2.9%. So quantization-aware training is still a useful tool. That's why we're building it. Now you may wonder, those were a lot of quantization types and tools. So which one should I use? So my recommendation is, if you are just starting, just start with try reduce float. That's the first one to try. It's just very easy to use. It doesn't require any data. The accuracy will probably be the same. And then latency, depending on the hardware, you might get some benefits, reduced latency. And then compatibility, basically everywhere you can execute floating point operations, you will be able to use it. The next thing to try will be the hybrid quantization. Again, there is no data requirements. The accuracy will be still good, probably not as good as float 16 in some cases, but it's still good. It will be faster than the reduced float. And basically, compatibility, well, everywhere that you have support for float and integer operations. Then the third one to try is the integer quantization with the post-training tool. So this one is a bit more complicated just because you need to provide a little bit of data. The accuracy will be worse or the same as hybrid, but the latency, this will be the fastest. And then it will also give you more hardware coverage. And then the last thing to try will be the integer quantization with quantization-aware training soon. And basically, this is there. This will be a little bit more involved because now you're doing training. You're supposed to have now a training setup, a training script, but the accuracy will be better than doing just the post-training version. And again, you get the benefits of being the fastest one and the one with more hardware coverage. So that was quantization. And again, all these tools we're trying to make it very easy to use, so it would be great if you try them out and give us some feedback. Then connection pruning. So what is neural connection pruning? Well, the way that we have implemented it so far in MINS is a training time technique that during the training process, it will start dropping connections from the neural network. And then these connections the drop connections basically just become zeros in the tensors that you're training, and then that means that you end up with sparse tensors. Now, sparse tensors are great because you can compress them and potentially execute them faster. So this is an example. This is, say, a tensor, how it starts randomly initialized. The dark values means values that are non-zero, and white means that values that are zero. And then as the training progresses, then it starts becoming sparser and sparser. And if you see, this tensor is basically we're removing most of the parameters there. The process for the API is very similar to the quantization that we're training API. Again, we're trying to bring some consistency to our APIs. So it's built on Keras. So it assumes that you have a model that is trainable on Keras. And then you're going to call our API to apply the pruning logic. And this, again, we're trying to make this as simple as possible. So the only thing that you need to define is the pruning schedule. Basically, when you want to start dropping these connections and until when and how fast, how aggressive you want this pruning to be. And then you just call our prune function, which again will modify your graph to add all the pruning operations internally. And then you just call your fit function and you train as usual. So basically you train as usual, and then once you train, you have two options now, or soon you will have two options. You can just take the same model, the TensorFlow same model, you can just compress it, gzip, and then the model will be smaller. And soon you will be able to convert it via TensorFlow Lite, and you will get also reduction in size and potentially some speed ups, depending on what prune configuration you're using and the hardware that you're targeting. So this should be done pretty soon. Now, what are the benefits of pruning? We've tried in a lot of tasks, like really a lot of tasks on image, speech, audio, and it worked pretty well. And like a lot of techniques that require a lot of hyperparameter tuning and careful restarting your models and things like that. But pruning has worked pretty well without a lot of babysitting. Then it has potential for speed ups depending on hardware support. And we also have pretty good results. Like we can make a lot of the parameters basically go away. We see 50 to 90% with negligible accuracy loss. And the other great thing is that it works well also with quantization. So a typical setup that we've tried is we train in pruning, and then we use post-training quantization. And basically, the accuracy is pretty good, and you get the compound benefits of both techniques. These are some older now results that we have when we launched this. This is an Inception B3. You see, we can get all the way almost to 90% sparsity with relatively small accuracy losses. And the other GNMT is neural machine translation, where again, we can take it to almost 90% pruning and also small accuracy losses. And we've done this for example, speech recognition. We actually had recently the Google Pixel event where the speech recognition models there use pruning and quantization, and we're able to have a model with server-side quality running on a phone, which is pretty good. Okay, so now I'll finally cover just real quick our roadmap. Like I mentioned, quantization, we're working on quantization training API, so that should be ready soon. And we are also working on our specs for quantizing RNNs, which are typically trickier to quantize, like LSTMs. Then I didn't include it there, but we're making some improvements to the hybrid quantization to be more accurate, particularly for convolution layers. And then for sparsity, we're adding support for sparse computation in TensorFlow runtime. Longer term, I don't know if you have heard about MLIR, but it's state-of-the-art compiler infrastructure. But this is particularly interesting to us because it's a better way for us to write these transformations. And at the end, like I said at the beginning of the talk, we're taking a model, we're transforming it into one program into another representation of that program. And some of the things that we want to enable is better targeted hardware. So our specifications are great because users can target our specification and execute in different hardware, but some users just want to zero out in one hardware and get the best out of it. So we're hoping that with the new infrastructure that we're building on top of MLIR, this should be possible. And finally, I really just want to encourage you to try it out and give us feedback. What techniques you would like to see. Research is, there is techniques popping up all over the place, and a lot of the work that we have to go through is calling what's useful and what's not, what is general and what is very specific. So we would love to hear your feedback about that, and also about the tools that we already have there in the toolkit. We're trying to make them as easy as possible to use. We know that we still have a long way to go, but any feedback that you can provide will be really, really appreciated. And I think there is a little bit of time for questions, if any of you have questions. Yeah. Thanks.
Hi, thank you for the presentation. I have a question regarding the training with integer quantizations. In the pipeline, is that going to be true quantization during training, or?
No, so right now the way, and by true I mean that you expect that all the operation happens in the integer domain.
Yes, yeah.
Not right now. That's something I really want to enable because I want to make training faster as well. But right now, the way that we're targeting is, I don't know if you're familiar with TensorFlow APIs, but we have this low-level API, unfortunately called fake quantization, that basically just emulates these losses. And that one is still basically what we do there is we quantize parameters, and then we dequantize them, and then we do the float operation. So that's what we are using right now. But yeah, longer term, we want to do true integer forward passes.
Okay. Thank you.
Hi. Can I go? Oh, I had one question.
Oh.
So after you do the quantization, is there a way that you can also visualize, the finished quantized model? It was one question, and I had another question. Let me think about it. But is there a way that you can also, the other question was, what sort of tools are you going to provide as far as sort of do like model correctness, and at least evaluate, how, whether this quantized model is sort of like functionally correct in a sense?
Yeah, so for visualization, again, it depends where, but for TensorFlow Lite, we have a visualizer so you can see the quantized model. I don't know if it will give you a lot of information depending what you're looking for. We also want to make our tooling a bit better because perhaps for whatever reason you want to get all researchy and start looking at the activations and how they change.
Sure, yeah. If there's like inserted ops and so forth,
I
could probably
for sure with the TF Lite visualizer, you can see how the graph changed.
Mm-hmm.
So the second question about correctness is really tricky because in my experience, the only thing that really works is to really evaluate on the real data that you care to run your model on.
Yeah, that's fair.
You know, like we try to do things like L2 norms to approximate, okay, versus the full precision one versus the quantized one.
Mm-hmm.
And it gives you a sense of, maybe some really catastrophic numerical errors, but otherwise is really just a guess, right?
That's fair.
Particularly depending on the output layers, categories are easier to quantize because the error is not very meaningful as long as you get the right category. Regressions are much harder because now you really care about the actual value. So it's an open
It's
problem.
a tough problem,
Yep.
yeah. Thank you.
I have a question about the results from the GNMT training with induced sparsity. I was wondering if you had any insights on why the training with 80% sparsity would perform better than the original version? Like if you looked at the...
The hand-wavy thing that we always say in these cases is some regularization happened. And yeah, and I've seen the same with some quantized models. I've never had the year to really sit down and try to understand what the reasons are for all this. Sometimes it's just because it's within the noise, right? It all depends on your evaluation set, right? If it's really not that big or not that meaningful, then these jumps are all possible. Like I've seen some models where, it looks great after you quantize it, then you throw in a new data set, say from speech recognition and noisier utterances, and then you clearly see the difference between one and the other. So it's a lot of it can be just noise.
Thank you.
Hi, you mentioned explainability, and a technique could be like saliency maps. Do you have any insights on how these techniques affect the ability to calculate the gradients, to calculate the saliency maps, for example?
That's something that we want to invest more, and we haven't had that much time to do it, and I would love for research to get more excited that are trying to understand neural networks, to also understand neural networks that have been approximated, but so far I haven't gotten any luck trying to get the people on that side excited about it. But yeah, I really don't have any meaningful thing to say because I haven't run many experiments around it.
Thank you.
Sorry.
Hey. Hey.
Oh, sorry.
Yeah. So what is the best way to handle fragmentation of hardware? So like quantization can depend on the target hardware. And more often than not in mobile phones like Android, you have so many types of hardware. So what are the best practices there?
Well, so one way that we tried to do it was, again, with these specifications. And I don't know to what extent it makes our hardware partners happy because we would like to be able to target their hardware in the most precise and efficient way, but that's one way that we try to address it, right? Like if, with our knowledge of somewhat what the hardware is there and what it supports, we try to create these specifications that, try to accommodate for everybody, which again, it's good and at the same time it's bad. Then longer term, and again, I don't want to say too much because I don't have a very concrete plan to share, but part of what we're building with the MLIR infrastructure is we want to be able to better target that hardware, better partner with hardware vendors to understand what are their hardware capabilities and better create these transformations that target that hardware. But we're really trying to make it much better.
So for now, does it mean like you go with the lowest common denominator, maybe like F316? Like imagine an Android app that you have to deploy on a lot of things.
And that's why we have all these different quantization types, right? Like we have 3 types, right? And soon, hopefully, we'll be able to even just mix and match those different types because, at the end of the day, it's a very arbitrary boundary. Then we say, this is all integer quantized, and this one is hybrid. And the reality, we should be able to take advantage of mixing and matching of precisions to get something better.
Thank you.
I have a question about pruning.
Yeah.
As a general rule on layers, operations are converted to matrix multiply because of their efficiency. With pruning, you're now passing in individual multiply operations one by one. There must be some crossover point at which you need to prune by 10, 15, 20% before you're crossing over and actually get an improvement. Thoughts on where that is?
So, and I don't know if this is exactly what you're asking, but so for example, our pruning API supports you specifying what the pruning structure is. So for example, we know that for CPUs, SIMD instructions, we typically have registers that can accommodate 16 values. So we know that if we want to speed up on CPU, we expect you to provide or to set the setting to say, oh, I want to prune in blocks of, say, 1/16, and that's how we can get speed ups on CPU, for example. And unfortunately, right now, probably it's going to be like hardware dependent, but that's one thing that you can do right now.